All right. So now the OBS is recording. My voice is also getting recorded as well. So now we can go ahead. And are there any questions about binary adding before we move on to binary subtraction? Questions anywhere? Are there any questions about the binary addition, the carry look ahead mechanism? Any questions regarding the carry look ahead mechanism? No questions? All right. So I'm just going to pop that up, okay? Just so that you guys can take a quick look and see if you have any questions, especially section 6, because section 6 is where the kind of some of the more heavy duty math is coming along, because we have the ki plus 1 defined by basically this becomes a gi term and this part becomes a pi term, and it relies on ki, and then by expansion we are able to figure out what k1 is, expressed only using the p and the g terms and k0. And then using expansion or substitution, we can also express k2 in terms of the g terms, the p terms, and also k0. And we can extend this to k3 the same way. And I believe last Thursday I also talked about kind of like a loop to evaluate the ugly long expression at the bottom. Is that correct? All right. So are there any questions about this particular module? No questions? Well, then I have a question for you guys. If you guys are not asking, then I'm going to ask. What is the whole advantage of carry look ahead? So let's not worry about the details or the proof that was presented here. What was the reason? Yes?
Faster for a computer to process?
Faster for computers to perform addition, yes. And why is it faster compared to carry ripple? Exactly. Okay, so if you generalize and you look at kn plus 1 in this expression, you can see how it only relies on the g terms, the p terms, and k0. How much time does it take to compute a p term, a single p bit? How many gates do we need to go through to compute a single p term? One gate, right? Because a p term is the disjunction or the or between the x and the y. Okay. What about g terms? How many gates do we need to go through to compute a single g term? One gate is an AND gate, right? Okay. And so if all the g terms and all the p terms require only one gate to compute, what about this nasty mess here? K0 and then the conjunction of I going from 0 to n pi. How many levels of gates do we need for just that term itself? All the way from the input pins, the x and the y pins. You need one level to get to the p terms, right? And then you need one more level to do the whole conjunction, including the conjunction with k0. So 2 levels of gates is enough to compute this particular term. What about this mess here? We need one level of gate to compute the p terms, one level of gate to compute the conjunction of all the p terms and the conjunction with gi itself, and then one more gate to compute the overall OR. But that gate can also be including this OR here. So that means 3 levels of gate propagation is enough to compute kn plus 1. Doesn't matter what n is. Is that okay? So if we assume the propagational delay of each gate is, let's say, 5 nanoseconds, okay? Then to compute k, whatever bit of whatever n is, kn plus 1 only requires 5 times 3, which is 15 nanoseconds to compute. You can have a 64-bit adder. It doesn't take any more time than a 16-bit adder. And that doesn't take any more time than a 4-bit adder. That is the whole idea of why carry look ahead is so useful. Now, in practice, on the other hand, you can't just have like 64 bits, all ended together using a single conjunction gate because, the fan out ratio sometimes doesn't support it. There are some other issues, like physical issues. But nonetheless, we are looking at a much faster computation compared to carry look ahead as a mechanism. So that's basically the main takeaway when you look at the big picture. When you look at the pine tree, that's the shape of the pine tree. That's what you need to remember about the pine tree of carry look ahead. Now, does it mean that it's not important to look into the actual mechanism, like this expression and also how we derived K1, K2, and K3? No, that is still important. But we should always keep in mind, why we are studying this. What is the significance of all of this? So do we have any questions about carry look ahead for binary addition? No questions? All right. So if there are no questions, I'm going to move on to subtraction. But before that, let me do something that I always forget. Obviously, not today. And that's passing the row sheet around. There we go. And I'm going to start with this side of the room. All right, so we'll do subtraction now. And since I just got my tablet up and running, that means I have to use it because otherwise, what is the whole point of fixing it and getting it to work? All right, so what you're seeing here is the screen of my tablet. So I can actually write notes. The glare is awful, there's just a lot of glare, but that's okay. We can still do it. There's a lag between what I write and what you see on the screen, but since I talk pretty slow, it shouldn't be a problem. Has anyone taken a class from Carol Lever? Professor Lever? No? She talks really, really fast. And I commented on that and say that I cannot possibly talk that fast because I cannot think that fast. Sorry? Yeah, she does talk pretty fast, right? Yep. All right, so we'll do some subtraction here. Okay, so subtraction, we'll do base 10 subtraction first. So let me pick something that's gonna be, okay, so we'll have something like this. 653 minus, I don't know, 459. Okay. All right, so that's a subtraction. It's all in base 10. Okay, so I'm hoping we can all do this without a calculator. Okay, some of you may be able to do it just mentally without actually using a piece of paper, but I want to illustrate important concepts, so we are going to do it kind of slowly and with very distinct steps. Okay, so the first row, so we'll name these rows the same way as with addition. So we got x and y. This is awfully slow. Okay, I might need to change the bit rate and sacrifice some quality, but we'll stay with this for now. So the first thing we need to figure out is what is 3 minus 9. Now 3 minus 9, okay, it's negative 6, but that's not what we want. We want to look at 3 minus 9 as a 4 with a borrow. Does it make sense? So we'll say this is a 4 with a borrow. But the borrow is borrowing from the next available digit, the more significant digit. So every time, even though we are saying we are borrowing 1, we're borrowing the quantity of 1, but the unit is not 1. The unit is 10. Is 10 times what the column that we are working with is representing. Okay? So that idea is basically say, oh, we only have 3 here. 3 is not enough to subtract 9, so we'll borrow 10. So now we got 13. 13 minus 9 is a 4. That's why we end up with a 4 here. So the way that I'm going to call this subtraction is 3 minus 9 has a result of 4, but a borrow of 1. Is that okay? So using this particular method, now I can do my subtraction in a non-conventional way, because now I can focus on 5 minus 5. So I look at this and say 5 minus 5 is a 0. And so far, no carry to the next digit. Fine, no problem. 6 minus 4 is a 2, and no borrow to the next available column. So I'm going to do it in this kind of strange way. Okay. The borrow from the unit is assumed 0 in most cases. So now I have a 4 here. 4 minus 0 is a 4. Okay. 0 minus 1 is a 9 with a borrow. Is that okay? Is this part okay? 0 minus 1 is a 9, but with a borrow. Now you have to be careful, because this borrow is coming from 3 minus 9. But this borrow is coming from 0 minus 1. So there are two sources of borrowing, because there are two subtractions for each column. Does that resemble addition? I think in addition there are two sources of carries, right? It's the same way. Okay, so now there are two sources of borrowing. So now I have 2 minus 1, which is a 1, with no overall borrow after the subtraction. So is that okay? Are there any questions about this particular process? Okay, assuming that there are no questions, I'll name these rows now. I'm going to name this row Q again. Okay, remember we had this row called Q for addition. I'm going to call it Q again in subtraction. So it'll be pretty clear why I call it Q again, but later on. The next row I call it K for addition. For this one, I'm just going to call it T for subtraction. Okay, this is basically all the borrow bits. And then the last one is called the sum, which is S for addition. And then for subtraction, I call this D for difference. So other than naming the rows a little bit differently, the process is pretty close to addition. Okay? So is that okay? All right? All right, I can't stand the lag. So I'm going to close this and configure it to be a little bit faster, and then because right now it's using slow high quality, so I'm going to take that bit rate down to maybe 2 megabits per second, and then see how that goes. The problem is my screen is too small. I can't even see the button at the bottom. So let me see if I can move this. Yeah, there we go. Save. And then have to move it back down again to activate the display. The first time it might not work. Yep. So you have to do it again. This time it should work. And the refresh should be a lot faster this time. There we go. Yeah, looks a lot faster already. Okay. So the next thing we want to do is to basically look at compare base 2 subtraction with base 10 subtraction. So what we'll do is we're going to take a look at base 10 subtraction. So with base 10 subtraction, you have a table of 0 to 9 in one axis and then 0 to 9 in the other axis. And then for each cell in between, you have to basically say, what is x minus y? Okay, what is the result of x minus y? And what is the borrow of x minus y? This table has 100 items, right? Because it was 0 to 10 is 10, and then 0 to 9 has 10 entries. 0 to 9 has 10 entries. 10 times 10 is 100. Now you can probably say, well, but we all know, anything minus 0 is the original thing. Okay, fine. So that you can subtract, one column or one row, so you still have 90 items. But because there's no symmetry, because subtraction is not commutative, you cannot just say, oh, we only have to remember 1/2 of the square because it is symmetric along the diagonal line. It is not symmetric because it's subtraction. It is not commutative. So this is a pretty big table. And you may not remember when you were in elementary school, maybe first grade or so, how long it took you to master subtraction. Okay? Now, if you have children, or if you have younger siblings or nephews or something like that, you can kind of check in with people who are just learning how to do subtraction, and figure out how long it takes to master subtraction. Because if I just ask you what is 3 minus 6, okay, well, how do you know it is 7 with a borrow? Because you have memorized it. Without memorization, what you need to do to figure out what is the result versus the borrow of a subtraction is, let's say 3 versus 6, right? So you have 3 here, and then you have 6 here. And when you try to do this subtraction, you realize that x is less than y, so the subtraction cannot work like this. Oh, this is still kind of laggy. Okay. So what do? You borrow. But how much are you borrowing? Depends on your base. In base 10, guess how much we're borrowing? We're borrowing 10. Exactly. So after you borrow 10, how much do you have? I'm going to use a different color to indicate the amount that we borrowed. So let's pick green. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the green part is representing the amount that you're borrowing. Okay? So suddenly you have 13. Okay? The quantity now you have available is 13 after the borrowing. So now you have enough to do the subtraction. Because now you can see, oh, after the subtraction, we have 1, 2, 3, 4, 5, 6, 7. Oh, cool. So that means in base 10, 3 minus 6 has a result. Okay, I'll write it this way. The result of 3 minus 6 is 7. The borrow of 3 minus 6 is 1. This 1 refers to the green stuff that we borrow from the next digit. This 7 refers to how much is left after we subtract the, I think it's called the minuend from the I cannot remember which one is the minuend, which one is the subtrahend. But the 7 is the result after the subtraction, after we take away 6 from 13. I can teach elementary school now. I remember distinctly when I was in elementary school, we got blocks. We got tiny little wooden blocks, and some are of length 2, length 3, length 4, and so on. And then that's how we actually learn subtraction, is to look at the blocks, okay, and go like, okay, now how much is left over, and then we measure the leftover using blocks of different length so that we can figure out the actual result of the subtraction. All right. This is going to take a elementary school person, a few weeks, okay, to memorize all this table, with a lot of quote unquote encouragement from parents and guardians. I know, because I needed that. Okay, without people actually reminding me to rote learn stuff like this, I would never have learned subtraction. Maybe the concept, but not the actual numbers. Okay. So now we look at base 2 subtraction. Okay, I just need a little bit of space for base 2 subtraction. So for base 2 subtraction, the table looks like this. 0, 1, 0, 1. And that's it. Because in base 2, those are the only 2 digits you have available when you perform any type of calculation. It's just 0 and 1. So it has 4 entries. Instead of writing those things in a table, I'll just write it out here. What do you think is the result of 0 minus 0? I got nothing, and nothing is removed, so how much do I have left? Nothing. Okay. What is the borrow of 0 minus 0? I got nothing. Um, Somebody asked me for nothing. Do I need to borrow? No. Okay. Okay, so let's look at the next one. I got, this is 0 minus 1. So this is the tricky one. 0 minus 1 in base 2, what do you think it is? Sorry? It's 1. Very good. It's 1 because I need to borrow. I got nothing. Somebody wants 1. I have to borrow. But in base 2, every time I borrow, I'm borrowing 2. So I now have 2. Take away 1. I have 1 left. Okay? So the result of 0 minus 1 is 1. The borrow of 0 minus 1 is also 1 because I do need to borrow. Okay? The amount that I have is less than how much I need to subtract from. The other ones are pretty easy. 1 minus 0. What is the result of 1 minus 0? 1. What about the borrow of 1 minus 0? Yep. All right. And the last one is 1 minus 1. What is the result of that? 0. And what is the borrow of 1 minus 1? 0 as well. Let's just focus on this table, this part here. Yeah, there's a lag. Okay, so this part here, haven't we seen this before? Isn't the R function returning exactly the same value as in addition? Turns out to be the same. Okay? So how did we implement R? Remember the lab from last time? From last Thursday? Exclusive OR. Okay, that's the easiest way to do it. So R of xy is just x and the exclusive OR with y. And by the way, exclusive OR sometimes is drawn like this as a symbol. It's a plus with a circle around it. All right. So borrow is the only one that is kind of not the same as what we have seen before. Okay? But it's not too bad because the only time b of xy is a 1 is when x is false and y is true. So what do you think is the Boolean expression to deal with that? Well, once again, I just spoke the answer within, I embedded the answer within the question itself. Yep. Not x and y, exactly. So b of xy is, well, I'll do it step by step, okay? Because what I said was when x is false and y is true, okay? That's what I said. But if y is Boolean, comparing a Boolean variable to true to confirm that it is true is really kind of redundant. So we don't do that comparison. We just say, oh, it's just y, okay? And for the same reason, we do not compare a Boolean variable with false to confirm that it is false. We just say that it is not x. And there's a conjunction in between, but if I use the shorthand, it becomes not x and y because I use the same symbol for multiplication to represent conjunction in Boolean logic or Boolean expressions. So are we good so far with this? That's the only thing that's different so far is, the borrow function is not the same as the carry function, but the result function is identical to the result function of addition. That is why in the previous slide, I used the same Q for the partial sum. Now it's the partial difference row. That's why I use Q, because Q by definition in the addition module is defined to be R of xy. And guess what? R is the same for subtraction, so I can keep the same symbol for that row. Any questions at this point about subtraction? Is that all good? Okay. So given this, let me switch back to my notes here. This time we're going to go for subtraction. The easiest way to switch from addition to subtraction is to change the module number from 283 to 284. Well, I remember the module numbers, that's why I can do that. So with this one, I kind of went through the same explanation, the same rationale, to go through all of this stuff, except I use uppercase instead of lowercase, but pretty much the same stuff. And I explained how the borrow function is really the negation of x, that whole thing, conjunction with y. So now we have to look at borrow propagation and also borrow look ahead. So as it turns out, there are two ways to perform a borrow. So when you look at ti plus 1, it is depending on the borrow of xi minus yi, but it also depends on the borrow of qi minus ti. Is that making any sense? Let me switch back to the tablet, because the tablet view would actually show you right away. Okay, this is a very good example. Let me see if I can use a color thing to help illustrate it. I'm going to use blue this time. Okay, so there are two sources of borrowing. The 3 minus 9 contributes to this borrow. Okay, there's a lag again. It's really, really laggy. And you find a way so it's not quite as laggy. So one source of a borrow is when we subtract y from x. Okay, what is the other source of a borrow? Is when we subtract the 1 from the 0. That contributes to that borrow. So when we subtract t from q, it can also contribute a borrow. Is that okay? That kind of seems to remind me of in addition, x plus y can contribute a carry, but then when q plus k, that can also contribute a carry. So we are now in the same situation as before, which is basically saying we have an arithmetic addition of the two sources of borrow. The question now is, can we use an OR instead, which is the same question that we asked ourselves when we are talking about addition. Okay? So now the question is, if I go back to my notes here, the question is ti plus 1, which is the borrow of the next column, depends on xi minus yi. That's one way to contribute a borrow. But it is also dependent on qi minus ti, which can also contribute a borrow. The only time an OR is not the same as an arithmetic addition is when you have both sides being ones. Okay? Then the arithmetic answer is 2, but the disjunction answer is 1. That's the only time when they don't jive. So if we can rule out that particular case, then we can use OR. Is that making any sense? Are we good? No? Okay. So if I want to turn this plus is a literal arithmetic addition. Okay? Because we don't know whether both of these can be ones at the same time or not. Okay. But if I want to turn this plus into an actual logical operation OR, I need to make sure that only one, up to one side can be a 1. They cannot be both ones at the same time. Is that okay? So how do we prove that? How do we make sure that only up to one side can be a plus, can be a 1, but not both sides being 1s? Well, let's try to figure out the logic. Okay? Let's say b of xi yi is a 1. According to the equation b, what does that guarantee? If b of xi yi is already a 1, what can we know about xi and yi? There's only, yeah. Xi is 0 and yi is a 1. Okay, so when b xi yi is a 1, we know that x has to be a 0 and y has to be a 1. Okay. Does that help me determine what is q? What is q? Q is the exclusive OR between xi and yi. That's by definition. Qi is xi exclusive OR yi. If xi is a 0, yi is a 1, the exclusive OR between those two is a 1. So qi is guaranteed a 1. 1 minus whatever has no borrow. Is that making any sense? So that way we have just guaranteed one scenario, that if the left-hand side of the plus is a 1, the right-hand side cannot be a 1. It has to be a 0. Okay. What about the other way around? What if the right-hand side is a 1? Does that guarantee the left-hand side is a 0? That becomes the opposite question. We have to answer both of those questions. Just because if one side is a 1, it guarantees the other side is a 0, does not mean the opposite. Okay, so we have to consider the opposite. Okay, so if qi minus ti give me a borrow of 1, what does that guarantee qi to be? It has to be a 0. So if qi is a 0 and qi is the exclusive OR between xi and yi, what does that mean? Okay, let me switch back to the tablet so I can actually illustrate it, what we're dealing with here. We need a new page. Okay, so we are now saying qi is known to be a 0. I'm just waiting for it to show up. The lag is kind of bad. I'm guessing if I restart it, it might be better, so I can give it a try. Let me just give it a try now, because this lag is killing me. Okay, so let me close this and then start the whole app again, because it might the setting may not take into effect until I restart it. So we'll give it one more try. Okay, so qi equals to 0 implies xi exclusive or yi equals to 0, because that's how qi is defined. Okay, but that in return implies one of two things. What do you think? If you look at the truth table, yep, go ahead. Exactly. Okay, so let's express that here. So that implies, xi equals to yi equals to 0, or xi equals to yi equals to 1. Right? Because that's the only two cases where the exclusive OR is going to be a 0. It's still laggy. Okay, can't fix that for now. All right, so, but the bottom line is, what is 0 minus 0 for the top case? What is the borrow of 0 minus 0? It has no borrow. Borrow is a 0. What about 1 minus 1? What is the borrow of 1 minus 1? It's also a 0. Oh, okay. So what that means is, when we go back to the equation, if we know that qi minus ti has a borrow, qi has to be 0. If qi is 0, it guarantees that xi and yi are the same. They can both be 0s, they can both be 1s, which also means the borrow of xi minus yi is also going to be a 0. So now this is the proof. Okay, it proves that if one side is a 1, the other side is guaranteed a 0. So that means they cannot be both 1s at the same time. If they cannot be both 1s at the same time, that means we can just get rid of the arithmetic addition and substitute it with a logical OR, and now we have the same scenario as a carry. That's how we solve the problem with a carry, and by removing the addition and replacing it with a disjunction. Cool. So now we get to this gigantic big mess of a proof. Okay. Why do you think this is important? Why don't I just kind of erase everything in between and start with ti plus 1, and then just equals to the negation of xi yi plus the negation of xi plus yi, and then the whole thing times ti. Show the work, but why is that important? I mean, you are not grading me, right? It is important to convince myself that I can show step by step that what I start off with ends up with the bottom expression. This is particularly important to me, so I'm going to use the next 3 minutes to tell you a story about graduate school. Okay. So when I started graduate school, there's a long story before that, but I'm going to start with the part that is of interest to us. So when I started my dissertation, my advisor told me about a particular theorem and say, Tech, this theorem was already done before you, so you can make an assumption that this theorem is true and start with that, okay? So I started with that for a few weeks, and then something just keeps gnawing in my head. It's like, it's an intuition. It's kind of like a gut feeling. As much as I think I do not have gut feelings, there's that sensation that I don't know about this theorem. It doesn't seem to be true all the time. Okay, so I approached my advisor and said, well, I'm not really sure about this particular theorem is true. Can I look at the proof of this so I can convince myself that, yep, okay, I can rely on it? So my advisor said, okay, so-and-so's master's thesis was on this particular theorem. Just look it up and you'll find the proof. So I did. Well, what I did was I looked up the master's thesis and tried to look for that proof. Except there was no actual proof. The theorem was stated, and there was another sentence below that that says, this is obviously true. Okay? When you're reading a technical journal or a technical paper like that, obviously this is true as a phrase is what we call famous last words. So I go like, no, this is not a proof, so I don't have a proof. So I spent an entire week to come up with a counterexample. So as it turns out, if you want to prove a theorem is not true, you just need a single counterexample where the theorem is false. And I did. So I went back to my advisor and go like, well, here's a counterexample. It is, proving that the theorem that I was relying on was false. My advisor looked at me and go like, oops. That was it. That was the one word response from my advisor was oops, because the committee for that particular master's thesis was identical to my own committee. It was exactly the same professors on both committees. So we better not say anything, right? But the story didn't end quite there. I went back to the lab. The AI, this is actually quote unquote the AI lab. So I went back to the AI lab and I shared this with another master's student who was working at the lab. So it was his third year. He was almost done with his master's thesis. And I told him about this, and he went ballistic because his master's thesis was based on the same theorem. I was only about 4 weeks into the whole thing. It's like, yeah, I can afford it. No problem, right? He was 3 years into it, and he was pretty much done at the time. So he just went ballistic. I felt sorry for the guy. But I had to tell him the truth. I mean, the truth is the truth, even though, sometimes it is not comfortable. But that is what drives me to use proofs as much as I can, not to only to illustrate it to you, how to prove and the importance of proof, but it is actually of personal importance to myself. So that's a little bit of a detour, but I hope some of you will remember this when you get to graduate school. And somebody hands you a theorem and just say, it is obviously true, just work with this. Yep.
Did your classmate have to do it all again?
Sorry?
Did your classmate have to do it all again?
I do not know what happened to his master's thesis. He got it done. I think they just kind of let certain things slide. So anyway, so let's look at this one here. I'll just do it kind of relatively quickly. From the first to the second row, it is just an expansion because that's what B is defined to be. Okay, so it's just by the definition of the borrow function. From the second row to the third row, it is how Qi is defined. In other words, I take this qi here, and then I substituted that qi with this nasty mess here. That nasty mess is really just exclusive OR, but I cannot use exclusive OR in this case. I have to expand it like this in order for the proof to work. From here to here is something that we haven't seen before. It's called De Morgan's Law. De Morgan's Law basically says you can distribute, quote unquote, distribute the negation on the outside of a disjunction into its components. So I apply the negation to the first term of the disjunction. I apply the negation to the other term of the disjunction. But when you apply De Morgan's Law, you have to remember to change the operator from disjunction to conjunction. Okay? If you're distributing over a conjunction, you have to change it back to a disjunction. Okay, so that's De Morgan's Law. So De Morgan's Law is particularly important for those of you who are going into computer or electrical engineering, because there are many, many cases where you need to apply that in order to get the result that you need. Okay? And then I apply De Morgan's Law again. I look at this expression, which is a negation on the outside applied to conjunction. So I distribute the negation to both of those terms. This is technically not yi, but not is canceling itself, so it's just yi left. The conjunction is changed to a disjunction because of the application of De Morgan's Law. I apply the same thing over here, and that becomes this. And then I use distribution. Distribution of Boolean algebra works kind of the same way as in usual algebra. So, that's nothing really too surprising here. And then I simplify this, okay? The negation of x and x is 0 for sure, because one side has to be a false, and when you have at least one side being false, the conjunction has to be false. Same thing applies to this guy here. Y and not yi has to be false, because, one of those two has to be a false, and you just need one for a conjunction to be false. The 0 gets simplified out, because when you say false or whatever, it is always just whatever. In other words, 0 or false is the identity of disjunction in Boolean algebra. Okay? So that's why I got rid of the zeros. So I got this term left, and then I work on the other side. Anything and true is what is that anything to begin with, and then you can say true or whatever is always true. Once you start with true, in the disjunction, you can OR it with anything you want. You always get true back. Is that making any sense? Okay? And to make it kind of even more silly, I'm ORing it with two TIs. Okay? As if ORing with one single TI is not stupid enough, I have to OR it with two TIs. Okay? But that's for a reason. It's because the next row applies distribution. So this one goes back to here, and then the TI is distributed to this term. The other TI is distributed to this term here. So you go like, why do that? I mean, it doesn't seem to make any sense. Well, then I moved this one over here. Just positioning is, it's moved over. And then I can do some factoring. So this thing is the same thing as this thing. I just factor out TI out of it. And then I do the same thing on the other side. I factor out TI out of the other term. And then I realize, oh, not xi is common to both of these terms. So I factor that one out to, with this one. And then on the other side, yi is common. Here's one yi, and here's the other yi. So they're common. They get factored out, just like with arithmetic algebra. You can do factoring just like that. Then I have yi or not yi left. Because between yi and not yi, at least one of them has to be, one and only one has to be true. So that means the whole thing has to be true. So that's why that simplifies to a true. Same thing applies here. Not xi or xi. One of them has to be true. So that means that also simplifies to a true. And true just doesn't do a single thing in a conjunction, so might as well not write it out. So that's why, that's how I ended up with this. And then I factor out the TI, and that became not xi or yi in parentheses, and then the whole thing and TI. So it's Boolean algebra, okay, but it's not that much different from algebra that you already know of. There are some special rules that only apply in Boolean algebra, but most of the rules that you already know in algebra still applies. Is that okay? I can kind of tell that half the class doesn't really like algebra, and then the other half of the class is like, yeah, algebra is my friend. Now I got a new friend. All right, so we ended up with this, and then I redefined GI and PI, so I have to emphasize the re part, okay, and that's why it's underlined. I redefined G and P because they are different from the G and P terms in addition. Just ever so slightly, it's not that big of a deal. So GI is now defined to be the negation of xi and yi, and then PI is now redefined to be the negation of xi or yi. In the case of addition, the xi was not negated. In the case of subtraction, the xi is negated. That's the only difference. But with that minor difference, I come to this form of ti plus 1. So ti plus 1 is now expressed as gi or pi and ti. Haven't we seen something like this before? In addition, it's the k, right? So ki plus 1 had about the same kind of definition. So do you think that trick that we did with ki plus 1 will work here? We figure out what is t1 first, and then use the t1, substitute it into the expression for t2, and then resolve that, and then take that into the expression of t3, and then resolve that. It works exactly the same way. Okay, because that's why we have P and G here. G actually stands for generate. P stands for propagate. So one term is quote unquote generate, which means it is introduced for a particular term. It is new to it. The propagation term means it is just staying with it, and that's why it's called a propagation term. But anytime you have a G and a P term, and then you have a quote unquote recurrence of the term on one side, it is just one index higher than the other side, this trick works. So they will always be, they always have a quote unquote closed form that looks like this, which we have seen, what, just about half an hour ago for addition. So as you can see, subtraction is not really that different from addition. The only change was what? How the P's and the G's are defined. And was it a major change? Nope, it was just the xi needed to be negated. So the same mechanism works, you just have to flip the xi to be negated. So you can easily turn a 3 by 3 bit carry look-ahead adder into a 3 by 3 bit borrow look-ahead subtractor, because there's only one place you need to change. Well, I would call it two places. Yep.
Is that why when we're way back in, was it 301 when we learned, I don't know if you guys learned 301 or 55, but when we learned addition and subtraction of binary, that there was the thing called one's complement, is that why?
Not quite. Not quite. Two's complement is how we represent negative values. So we will get there, but it doesn't relate to this part yet.
Okay.
Yep. All right. Well, this is binary subtraction. Easy peasy. Once you understand binary addition and the mechanism of carry look ahead, subtraction is pretty much a mirror image of that. Everything that you knew about carry look ahead in an adder applies pretty much the same way in subtraction. So are we good so far with binary subtraction? That was quick, less than an hour. And that includes a review of the earlier material too. Are there any questions? Because if you guys don't ask questions, I'm gonna go full speed. But I do allow plenty of time and opportunity for anyone to ask any questions at any time. So it's kind of up to you guys to ask questions, to clarify, to slow me down, and have me to kind of re-explain things in a slightly different way. No questions? Okay, I do have to confess one thing. I am not a mind reader. If you have a questions brewing in your head, I cannot read that. You have to raise your hand and let me know. Okay? All right. So if that is out of the way, we actually get to some of the fun stuff. So the next thing, which you learned in 301, CISP 301, right? So that means you come from Sac City.
Yeah.
Because only Sac City has CISP 301. It is CISP 300 here. And I don't think we talk about 2's complement in CISP 300 here. So the content is a little bit different over at Sac City. Sac City is the only one that has 301. The other 3 colleges have 300. All right. So the next question now is, how do we represent negative values, but using only zeros and ones? Okay, because it seems like a pretty stupid question. How do we represent negative values? All right, let's switch back to the tablet here. So how do we represent negative values? How about this in base 10? Okay, it takes a little bit of time to refresh. There you go. So negative 35 is just 35, but then we put a unary subtraction operator at the beginning to indicate that this is 35 as a magnitude, but in the other direction. Okay? Okay, we know this. What about base 2? Well, it seems like base 2 is the same thing. So if 1011 is representing 11, the quantity of 11 in base 2, to represent the negation of that, which is negative 11, can't we just do something like that? And just do the same thing, add a little unary minus to the left-hand side, and then we are done. Well, the problem is there's no negative symbol in transistors. So we have to kind of limit ourselves with only zeros and ones when we talk about representing anything in a computer. Everything has to boil down to just zeros and ones. Okay, then why don't we just use a bit here? If it's a 0, it means it's not negative. If it's a 1, that means it's negative. Well, that might work, except you will have to redo the adders and the subtractors to deal with it, which is a hassle. Okay, so we don't want to deal with a hassle when we don't have to. So that's why we have to do this in 2's complement. Okay, so that's the reason why we are going to get into this slide that talks about signed value representation, which is about how we represent negative values. All right, so we can start with section 2 is kind of what we just talked about. Everything needs to be represented in zeros and ones. We do not have, a transistor cannot represent a negative symbol. So section 3 is basically where we want to start. Okay, we are talking about arithmetic negation first. So there are a few things about arithmetic negation that we kind of need to know. The negation of a number is the number itself. In other words, arithmetic negation is its own inverse function. Is that okay? The other thing that we also know is a number plus its own negation is going to be 0. Right? Okay. And then another one is saying, if you want to compute x minus y, one way to do it is to figure out what is the negation of y and then add that amount to x. They should come out to be the same. Okay, so nothing really surprising here. And then the next slide, or the next section, talks about the number circle, which I think is a very important concept, but I was too lazy to draw a picture and put it into my notes. So we can do it here using the tablet, even though it's kind of laggy. we can still do it. Let me do it one more time and change the bit rate to even a slower bit rate and see if that helps. Okay. So we're down to 2 megabits and it's still really slow. So we'll try fast, lowest quality and see what happens. It's a problem when my screen is too small and I can't display the entire window. Okay, let me move this back down. And the first time it's going to crash, the second one will connect. Yep. Okay, so let me draw a circle. It's called the number circle. You guys are all familiar with a number line, but in this class, in computer science in general, instead of drawing numbers on a line, it is a circle. Why do you think it's going to be a circle? What is the difference between a line versus a circle? Okay, how about you go ahead and then you. There's no end to a circle. Well, but it does go back to a certain point, right? You go around and you arrive to the same point that you started off with. Yep, go ahead. Okay. Yep. So what we'll do is we are going to talk about, let's say, a 3-bit number, okay, because that's going to take less time to draw the whole circle. So the way that I do it, which is just my convention, okay, there's no one that says it has to be like this, is to put 0 at 12 o'clock. Yeah, it's still really laggy. In fact, it might be even more laggy than before. So I put 0 here, and then we just draw the other slots available, like so. Okay, and then we number these. Okay, so next one is 001, 010, 10. Whoops. I need to go back. Undo. Where's my undo button? Nope, that's not undo. Oh well. 011, 100, 101, 110, and 111. Okay. So I just have to wait for this to update. It seems to do it in bursts. I don't know why it's doing it in bursts. But I'll figure it out. Anyway, so this is a number wheel instead of a number line, because with 3 bits, guess what? These are all the possible binary patterns that you can actually represent if you're only given 3 bits. Is that making any sense? And they can be used to represent whatever you want it to represent. But since we're dealing with numbers or values, it kind of makes sense that 000 would be used to represent the quantity of 0. Okay, that just kind of seems to make sense. So I'm going to say, okay, let's make this guy represent the quantity of 0. So the top number, or the number on the outside, 000, is the state of the transistors. Okay, low voltage, low voltage, low voltage. Okay, the number in the inside is what we want that physical state to represent as a value. 0 means nothing, nada. Okay, none. Okay, so it seems to make sense. The next one is going to be a 1, and then a 2, 3, 4, 5, 6, 7. Okay, there we go. Does that make sense? Okay. I don't see any negative numbers. Shucks. But if I look at this, the direction here, it seems like, when I go in a clockwise fashion, I'm increasing by 1. if I go in the counterclockwise fashion, I'm decreasing by 1. Does that make sense? Like, from 2 to 3, that's, just clockwise 1 slot. From 5 to 4, it is counterclockwise by 1 slot. Okay? So using that generalization, if I wanted to represent negative values, where do you think -1 should be? It should be at about 10 o'clock, right? Well, 10:30 to be exact, okay, if you look at the hour hand. So 10:30 is where it needs to be. So we'll just use a red color here to say that, if we want to assign a representation of -1, this is the place to put it because it is counterclockwise from 0 for 1 slot. Right? Okay. So that means, I can use this to kind of fill out some of the other slots, -2, -3, -4. Does that make sense? But I'm going to stop here. The reason why I stop here is because now I have an equal number of negative values and non-negative values. 0, 1, 2, 3 are non-negative. -1, -2, -3, and -4 are negative. So I'm going to dedicate, or I'll assign half of the patterns to non-negative values and the other half to negative values. But instantly we have a problem. It's like, so what is exactly 110? Is it 6 or is it -2? Which way is it? And the answer is, you don't need to know. Okay? So this is very different from, all the programming classes that you have taken where, you have to know whether it's signed or unsigned. In assembly programming, at least, with adding and subtracting, we don't really need to know what it's representing. All we need to know are the patterns, the bit patterns on the outside. What values they are representing, we don't actually need to know. What? That doesn't make sense at all. So let's do some calculations, okay? Now with 3 bits, I can only do a limited amount of calculations, but nonetheless, we can do it. So we'll go ahead and do some calculations. And let's see, I'm going to change my pen back to black. And we'll figure out something like 1, 1, 1 minus 0, 1, 0. Like that. Base 2. Okay, so this is a base 2 subtraction. So most of you can see, oh, that's easy. I mean, there's no borrow anywhere. So the 1 minus 1 is the only one that results in a 1 in the difference. The other 2 bits will just end up with a 1 because they are both 1 minus 0. Okay, so we end up with 1, 0, 1. Okay. Remember what I said about, we don't need to know what 1, 1, 1 is representing because it could be -1, it could be 7, right? So now we write down those representations on the other side. We go like, okay, so let's say we look at the numbers in an unsigned way, which means we ignore all of the negative values. So 1, 1, 1 is going to be representing 7. 1, 0, 1 is representing 2. And we should get 5 back. Is 5 represented by 1, 0, 1 in base 2? Well, let's try to figure out. 1, 1, 0, 2, 1, 4, which means it is 1 plus 4. Oh yeah, that's 5. Okay, cool. What about the negative side? What if we take those, kind of red numbers into consideration? Well, let's check it out. So if we do want to take the red representations into consideration, 1, 1, 1 is representing -1. 0, 1, 0 is always 2. There's no red representation, so that's just 2. And we should end up with -3. What is the bit pattern of -3? It turns out to be 1, 0, 1. Magically, right? Cool. So if you ignore the quantities actually represented, the logic or the circuitry for doing the subtraction is universal. Okay? It works for unsigned numbers. It also works for signed numbers. This is the main reason why we choose to use 2's complement, which is what you're seeing here, to represent negative values, because they can share the same circuitry with signed calculation as far as adding and subtracting is concerned. Is that okay? Because otherwise we'll have to have another discussion of adder circuits and subtractor circuits and so on. But as it turns out, with 2's complement, we can use exactly the same adder, the same subtractor. They work just fine. Not a problem. Are we doing okay so far? All right. So what about that 2's complement thing? Where is that name coming from? So let's go back to the circle and just kind of focus on the circle now and go like, why is it called 2's complement? Well, there's a particular reason why it's called 2's complement, but how do you think I came up, what is one way to come up with this -1, -2, -3 based on the other numbers that we have? This is 3 bits, right? These are all 3-bit numbers, and 2 to the power of 3 is 8, okay? So you keep 8 in mind as a constant, and then you look at the numbers on the wheels, and you go like, the ones that have 2 numbers, one in black and one in red, how do those 2 numbers relate? How do they relate to 8, which is 2 to the power of 3? What do you think? Okay, you can call it absolute number, but there are other ways to do it too. So let me see if I can work it out like this. So if I call the one number that is in black, let's call it x, and then the number that is in red, we call it y, okay? And we know 8 is important, so 8 is what? Let's not use absolute number, okay, because absolute value is, you can't move it around in algebra easily. So we have 8 equals to, I know it has something to do with x and y. I mean, that part is kind of obvious. So how does it relate to x and y? Yep. Well, you subtract y from x. Okay, let's see if this works. Does it work? Because y is negative. Y is the red part, it is negative. So let's say we are looking at this one. X is 7, y is -1. 7 minus -1 is 8. 6 minus -2, 8. 5 minus -3, 8. 4 minus -4, also 8. Cool. Okay. So I can now move things around a little bit. So what I'm going to do is I'm going to move things around, and I have to remember which way they're supposed to be moved around. Okay, so we can now say 8 minus x is -y. As I said, some of you enjoy algebra, and you will enjoy this particular class. And those of you who hated algebra may not enjoy this class as much. But can we do this? Okay, because we are just subtracting x from both sides of the equality. I mean, it's no big deal. Okay. That's kind of interesting, because this 8 minus x is, guess what? 1. 8 minus 6 is 2. 8 minus 5 is 3. 8 minus 4 is 4. So whatever quantity is left on the left-hand side of the equality is, quote-unquote, the magnitude of the number to the right-hand side. That's kind of cool. So where do you think the 2's complement concept comes in? Okay, this is really profound, because what it means is, in order to find out the bit pattern of a particular negative quantity, okay, so y itself is a negative quantity. If you want to find the representation of that, you just have to go through this math to find out, the bit pattern of that negative, the representation of the negative quantity. So 8 is a cool number, but how many bits do we need to represent 8? No. How many bits, how many digits do we need to represent 8 in base 2? 4, yeah, 4 digits, because 8 is 1, 0, 0, 0. Okay? So that means, if I want to do all of this using a 3-bit representation system, I can't deal with the 8. Okay. So if I cannot deal with the 8, what can I deal with? So the bottom line is, we can also look at this in a slightly different way. So we can say, x 8 plus y equals to x. Okay, it's the same thing. I just kind of flip things around, but the idea is we want to figure out x. We are given y, we have to figure out x. That's what we're trying to do. So now we reverse it and say x is 8 plus y. But we cannot do 8 because 8 cannot be represented as 3 bits. It is a 4-bit number. Okay? What is 8? Isn't 8 the same thing as 7 plus 1? Okay. Okay. Would that work? Sure. Oops. Would that work? Every moment is a cliffhanger. Okay, would that work? That'll work. Okay, so let me get this straight. To figure out the binary representation, which is x, okay, of a negative quantity, we just have to add the negative quantity to 7 and then add 1 to the whole thing. Okay. I still don't understand why it's called 2's complement. When you subtract, okay, y is always a negative quantity, so that means 7 plus y is actually the same thing as subtracting the magnitude of y from 7. Okay? What is 7 in binary? 1, 1, 1, right? And if you subtract anything that is 3-bit wide from 1, 1, 1, would you ever end up with a borrow? No, you don't end up with a borrow, which, okay, that's kind of interesting. So I'm going to do it on the left-hand side here. So 1, 1, 1 minus, I'm just calling this, y0, y1, and y2. It's going to end up with as what? This is a special subtraction because we know we are subtracting from 1, 1, 1 as a base 2 number. But what do you think is going to be the first digit of the difference? Yep. The logical negation. Oh, okay. So this is the negation of y0. Okay, wait, hold on a second here. How did we jump from subtraction, which is arithmetic, into logical operation? But it does make sense. Because if y0 is a 0, 1 minus 0 is a 1. And guess what? 1 turns out to be the logical negation of 0. Okay, what if y0 is a 1? 1 minus 1 is a 0. 0 is the negation of 1. Okay. So that means the next digit is going to be the same way. Not y1, not y2. Is that okay? We call this Bitwise Not. I'm not sure how many of you learned Bitwise Not or the tilde symbol in cisp310, but this is what we call Bitwise Not. Bitwise Not is also called 1's complement. Okay, so this is 1's complement. Okay, but we mentioned something about 2's complement, right? So where's the 2 coming in? The 2's complement comes from this plus 1 here. So 1's complement plus 1 is called 2's complement. Okay? All right, so let me just clean this up a little bit. Okay, so we'll say I use C2 to denote 2's complement. So the 2's complement of a bit pattern X is the same thing as 1's complement of the bit pattern X plus 1. Yeah, here we go. And coming along. Okay, there we go. That's 2's complement. And I claim that 2's complement of something is the same thing as negation. So let me make this really kind of bold claim that C2 of X is really the same thing as the negation of X, except one is the bit pattern, the other one is the actual quantity. All right? I'm not buying this. Let's give it a try. Okay, so we'll work this out. So we'll say, okay, let's come up with the 2's complement of 2. 2 in binary is 0, 1, 0. Okay? And what do you think that is? Well, let's go with the definition. This is the 1's complement of 0, 1, 0 in base 2 plus 1. Okay, come on. Okay, that's just by definition. That's the definition of 2's complement. Remind me again, what is 1's complement? It's called bitwise not, right? And bitwise not simply means if you see a 0, flip it to a 1. If you see a 1, flip it to a 0. That's all we're going to do. So bit by bit, we're changing it to 101 plus 1. So that becomes 110 in base 2. Okay, I'm waiting for the tablet to catch up. Okay, so, but I'm also saying 110 is used to represent negative 2 in this case. So let's look up that wheel and see whether 110 is actually negative 2. Yep, okay, we can see it already. It just takes, exactly. Yeah, we can see all those bits being hurried. So 110 as a bit pattern, high voltage, low voltage, turns out to be representing the quantity of negative 2. So 2's complement actually works out. So as an exercise, because we are almost running out of time today, if you apply 2's complement to 2's complement of something, what do you think you should get back? The original thing, because I claim that 2's complement is the same thing as arithmetic negation. So if you apply 2's complement to the 2's complement of X, you should get X back. Okay, that's one thing. If you add X to the 2's complement of X, you should get 0. If you have X plus the 2's complement of Y, you should get X minus Y. All of those things that we talked about earlier about arithmetic negation, they should work with 2's complement, because I claim that 2's complement is identical. It does the same thing as arithmetic negation. So are we doing okay so far with this concept of 2's complement? How many people are still kind of hung up about, but I get that part. The mechanical part is not a problem. Okay, the pine needle I get. Okay, I just don't get the pine tree of how 101 in this case can be representing 5 sometimes, and it can be representing negative 3 some other times. And how does that work? I mean, so exactly what is it? Yep. Okay. So to answer that question, I'll give you a little seed so they can think about it. What is that? Okay, so what I'm giving you is a whole bunch of blue pigment, on a whiteboard, right? And if I do it on the tablet, it becomes a whole bunch of blue pixels, surrounded by white pixels, right? That by itself has absolutely no meanings whatsoever, right? Nothing other than, yep, a bunch of blue pigments on top of a white background, okay? So without any context, if I don't say about any context, we go like, I have no idea what it is, but I can see I can see the arrangement of all the blue pigment in a vertical way, and that's the best you can describe it. You cannot say what it is. In the context of, this thing, am going to class. Oh, that's I, okay? It's the uppercase I character, right? But it can also be lowercase l. It can be 1. It can be vertical bar symbol, okay? But without context, we don't know which way to look at it. Is that okay? Same thing here. 110 is nothing more than 3 transistors right next to each other, having high, and low voltage as their output. What does it mean? I have no idea. Just like, the blue pigment arranged in a vertical way. It has no inherent meanings whatsoever. Okay? It's nothing more than just, 110 as bits. Okay? The only time it actually has meanings is when you need to compare. Then you have to think about, if you're comparing, let's say you're comparing 110 with 0, then you have to know, if 110 is representing 6, then 110 is greater than 0. But on the other hand, if 110 is representing -2, it is less than 0. The result is now important. Then you need to know which way you should look at 110. But until such time, if you want to do addition, not a problem, okay? You just treat 110 as 110. Go through all the same logic, the same transistors that we have talked about for binary addition or binary subtraction, whatever, okay? It doesn't really matter. It's only when you need to make a decision, okay? When you have a conditional statement, when you have a condition of a loop or something like that, you have to compare to decide, should I go for another iteration? Should I go to the then branch or the else branch? Then it becomes important to go like, is 110 signed, which means it has a value of it's representing -2, or is it unsigned, which means it's representing the quantity of 6? Then it becomes important. But only then it becomes important. Is that okay? So when you just look at 110 as a bit pattern, don't try to think about which way it is, because it's not time yet to determine which way it should be. Is that okay? So I'm planting that little seed in your head so that you don't you don't trap yourself into thinking, but which way is it? Is it a quantum thing where sometimes it is this and sometimes it's that? No, it is not quantum or anything like that. It is just unassigned until we need to interpret with a context. All right? So we do have a lab today, which is the second part of the lab from last week. So I hope you have your file available from last week, because we are continuing with that particular file today.